Hello everyone, welcome to this new lesson on the topic trends in periodic table. Okay, so this particular topic is very important regarding your JEE main examination because every year around 3 to 4 questions, that is 12 to 16 marks, comes directly from this topic, that is trends in periodic table. In this particular topic, we'll study about different kind of trends that we follow or that we have in a periodic table and try to solve some questions from it. Okay, so without wasting any time, let's get started with the lecture. Okay, so the very first thing is properties. Before understanding the trends, we need to understand the properties. It is very important. Okay, so let's start with the very first property that we have here, effective nuclear charge, or Z effective, also known as Z star. What it is? The net positive charge experienced by the outer electron in a polyelectronic atom is called Z effective. Let me explain this to you with an example only. Okay, let's take some good example. Suppose you have got nitrogen here with atomic number of what? 7. So 1s2, I hope you know this, 2s2 and 2p3. Okay, so the first orbital has got 2 electrons and the second orbital has got how many? 5 electrons. Okay, so now let me draw the nucleus here. This is our nucleus and these are the orbitals. Okay, this is the first orbital with 2 electrons and second orbital with 1 2 3 4 and 5 electrons. Okay, let's suppose we are taking this particular electron. This particular electron will face attraction force from this particular nucleus because of positive and negative charge difference, and these electrons in the inner shell will repel this particular electron. So repulsion. Now because of this repulsion, the net attraction force that this particular electron is facing from this nucleus will get reduced, and this reduced net attraction force is called Z effective. Got it? Okay, so this is our Z effective. It happens because of screening effect or shielding effect. What it is? The decrease in force of attraction between nucleus and the outer electron by the inner electron. As stated in the example, this is called screening effect. Okay, but you have got a formula. Okay, we have a formula to calculate this Z effective because we can't rely on such theories only. We need some mathematical equation. So the formula is Z effective is equal to Z minus sigma. Z is atomic number, we already know, and sigma is called shielding or screening constant. Okay, sigma is known as shielding or screening constant, and this particular constant depends upon various aspects that we are going to cover in upcoming slides. Okay, here's a better pictorial representation of the shielding effect. This is our outer electron getting attracted towards nucleus because of positive and negative charge, but these inner electrons are repelling it outside. So the net attraction will be what? Z effective. Got it? Let's move further. Okay, so there are various ways of calculating Z effective. Okay, various aspects or various ways to calculate this particular Z effective. Or to be precise, Z effective is equal to what? It is equal to Z minus sigma. We, in general, in questions, Z we know the atomic number of the element we are working on. So we need to find the sigma only, and there are various ways to find the sigma as stated here. So this sigma can be found out by the help of Slater's rules. What is Slater rules? Slater rule is basically divided in two cases. Okay, so first we'll study case 1 only. Okay, so case 1 states that if electrons in question resides in S or P subshell. For example, we have to find Z effective of any electron and it is in S or P subshell, then this particular case will be implemented and these four rules will be taken care of. Okay, this is D. So first A is all electrons present in shells higher than electrons in question contribute 0 to sigma. For example, here is our nucleus, these are our shells. Okay, here 2 electrons, 2 electrons and 2 electrons. Suppose we have to find Z effective of this particular electron. So the contribution to the sigma by these 2 electrons will be what? 0, because they are greater, because they are in shell higher. So their contribution will be what? 0. Okay. All electrons present in same shell contribute 0.35 to sigma. For example, this particular electron will contribute how much? 0.35 to sigma. All electrons present in n-1 shell contribute 0.85 to sigma. So this is our n shell. So this is our n- shell. And contribution by these 2 electrons will be what? It will be 0.85. Got it? All electrons present in deeper shell contribute n to sigma, 1 to sigma. That is if there are 2 shells more here with 2 more electrons. So their contribution will be what? Their contribution will be whole 1 to this particular electron's sigma value. Got it? It might sound too much of info, but we'll solve some example to help you go through them. Okay, so here is our example 1. Find Z effective of last electron of chlorine. Okay, so what is the atomic number of chlorine? It is 17. So 1s2, 2s2, 2p6, 3s2 and 3p5. Easy peasy. 2 electrons in first shell, 8 electrons in second shell, and how much here? 7 electrons in third shell. Now we have to calculate Z effective for the last electron of chlorine. That is, obviously that electron is in this particular shell or orbital. So according to the formula, what it stated, let's go back, the contribution by electrons present in shell higher than the electron in question. So there are no shell higher in our particular case, because it's last electron, so obviously from the last shell. Okay, so it is not valid here. All electrons present in same shell contribute 0.35. So contribution by 6 electrons left here. Okay, contribution by 6 electrons, because 1 is being considered for the question only. So 6 into 0.35 will be contribution to sigma by these 6 electrons, followed by 8 electrons. It is n-1. This is n. This is n-2. So contribution by these 8 will be what? 8 into 0.85 as stated before. And contribution by further electrons will be what? It will be whole 1. So 2 into 1. Calculate this, you will get the value of sigma. Now we already know that sigma is equal to what? Sigma is equal to Z effective. Z effective is equal to Z minus sigma. So we know what is Z. Z is, for chlorine it is 17, and sigma we'll calculate from this. Just put it here, you will get your Z effective. I'm not doing it. It is very easy. Do it on your own. Got it? Got the question? Let's move on to next example. Okay, find the Z effective of 9th electron of calcium. Okay, so calcium's atomic number is what? It is 20. So it becomes 1s2, 2s2, 2p6, 3s2. I hope you guys know this. 3p6 and 4s2. Yes. So first shell has how many? 2 electrons. Second has how many? 8 electrons. Third has 8 electrons, and fourth has 2 electrons. We have to find the Z effective of 9th electron. Now obviously the 9th electron will be in this particular second shell. Okay, so this second shell will be our nth shell, and this will be n-1. Now as stated before, the contribution by shells higher than will be what? Will be 0. So their contribution, these 10 electrons will contribute 0 to the sigma. The contribution by leftover 7 electrons will be what? 0.35, and contribution by these electrons will be what? 2 into 0.85. Simply add these, you will get the value of sigma. Then we know Z effective is equal to what? It is equal to, in this particular case, 20 minus sigma. You will get your answer. Very easy. Got it? Let's move further. Okay, now comes the second case. What is second case? If electrons in question resides in D or F subshell. In earlier case it was what? It was S or P subshell. Now here we have D or F subshell. In those particular cases, these things are to be followed. A, all electrons present in shells higher than electrons in question contribute 0, just like the last one. All electrons present in same shell contribute 0.35, just as the last one. Last one, all electrons present in n-1 and lower. This is changed here. N-1 and lower shells contribute 1 to sigma. Okay. Earlier it was n-1 0.85 and lower than that was 1. But here both are combined and their contribution will be 1. Got it? Very easy. Not major changes. Let's solve an example. Find the Z effective of 23rd electrons of Fe. Okay, so Fe's atomic number is what? Fe's atomic number is 26. So it will be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 3d10. I have written 4s2 here and 3d10 here so that you understand that third orbital is together here. It will help you to solve the question. Okay. First orbital has got how many? 2 electrons. Second has got 8. Third has got 14. This is 6. And fourth has got 2 electrons. Now we are supposed to find the 23rd electron. Obviously, if you see here, 23rd electron will belong to this particular third orbital. Okay, so the contribution by these 2 electrons will be what? It will be 0. Contribution by 13 electrons here will be what? 0.35. And contribution by this entire n-1, including n-1 in the all deeper subshells, will be what? Whole 1. So 10 into 1. Calculate it, you will get your sigma. Then very easy, just subtract the sigma from the atomic number, that is 26. So 26 minus sigma. Okay, so the second properties that we have is atomic radius. This atomic radius is divided into 3 types. Okay, we have got 3 types of atomic radius. We'll study each one of them one by one. Let's start with the covalent radius. What is covalent radius? It is 1/2 of the distance between 2 nuclei of like atoms bonded by a single covalent bond. Okay, let me just draw a diagram for you. These are 2 like atoms, X and X, and these are the nuclei A and B. So the distance between these nuclei, so the distance between DAB, its half is equal to the radius of this particular element, this particular atom X. This is covalent radius. Got it? Very simple. This is the formula. Okay, now let's suppose that we have got unlike atoms. Okay, unlike atoms. Here we have X and X, but suppose we have got X and Y, then what? In that particular case, we have got 2 further cases. Okay, they are called heteroatomic molecules, obviously, because these are different. So they are heteroatomic, and we have got 2 cases for them. The very first case is when delta X, that is electronegativity's difference, the difference in the electronegativity of atom. When that difference tends to 0, that is our first case. In that particular case, let me just redraw the diagram. X and Y, these are the nucleus A and B. In that particular case, this DAB is equal to what? It is equal to Rx plus Ry, the radius of X plus radius of Y. This is our formula. Got it? Very easy. Let's move on to next. For case 2, that is when electronegativity's difference is not tending to 0. In that particular case, how we do it? Let me just redraw the diagram. In that particular case, now we have got 2 formulas, okay, to get the value of X and Y, and we'll be looking at those formulas in the next slide. Here it is. These are the 2 formulas that we use to find the relation between radius and the distance of both the nucleus. What are the formula? First we have got Stevenson and Shoemaker formula. What it is? It is d of AB, that is distance between both the nucleus A, B, X and Y. It is equal to d of AB is equal to radius of A plus radius of B minus 0.09 delta X. What is delta X? It is nothing but difference in the electronegativity of both the atoms. Got it? Second, we have got Porterfield. It is a revised equation, okay, better equation. It states d of AB is equal to R of A plus R of B, same. The factor gets changed here. It is 0.09, it is 0.07. Same delta X, the difference of electronegativity. Okay, so if in question nothing is stated, you will use this particular thing, Potter field. But if it is stated to use this particular one, you will use that only. Got it? Let's move further. Okay. So now we have got the second type of atomic radius, that is metallic radius. What it is, it states that one half of the distance between two nearest neighboring atoms in metal crystal. Okay, metallic radius is one half of the distance between two nearest neighboring atoms. Let me just draw a diagram here as well. These are two, okay, they will be separated here. These are two atoms, neighboring atoms. These are the nucleus. So radius of x will be what? It will be d of AB upon 2. Got it? Just like the covalent one. Very simple. Okay, let's move further. Lastly, we have got van der Waals radius. It is one half of the distance between nuclei of two nearest neighboring molecules. Suppose we have got two molecules, X and X, Y and Y. So the distance between nearest two nuclei, these two nuclei will be nearest to them. So their distance d of AB is equal to, when divided by 2, will be equal to radius of X. This is van der Waals radius. Got it? Very simple. Now there is a relation between these three radius. Okay, a relation between three radiuses that we have just discussed. What is the relation between these three radius? It is that van der Waals radius RV is greatest or is greater than all three of them, followed by metallic radius, followed by covalent radius. It is very important. Remember this particular thing. The van der Waals radius is greatest or greater than these two, followed by metallic radius, followed by covalent radius. So the first question that we have is, Hardik Pandya went to meet his brother Krunal Pandya, where he saw that Krunal was studying from Ansar sir's chemistry book. Krunal could not find the theoretical value of the bond length of the HF molecule. However, he found the radii of hydrogen and fluorine to be 0.388 angstrom, 0.72 angstrom respectively, and the electronegativities of fluorine and hydrogen to be 4 and 1 respectively. Find the HF bond length according to, now here it is stated, Stevenson and Shoemaker formula. Okay, what the formula was, let me just remind it for you. D of AB is equal to R of A plus R of B minus 0.09 delta X. Got it? This was the Stevenson and Shoemaker formula. Okay, let's solve it from this formula only. So in question we have to find what? We have to find D of AB only. And we are given RA, RB and difference. As we are given the electronegativities as well, so we can find the difference. Okay. So R of AB is what? R of AB is 0.38 angstrom. R of B is 0.72 angstrons minus 0.09. The difference of electronegativity will be what? It will be 1.9. So it will become 1.1 minus 0.17 equals to 0.93 angstrom. This is the question. Got it? Simply put the value in formula and you will get it. Okay, let's move further. Let's move on to next question. The CC single bond length is 1.54 angstrom and that of ClCl is 1.98 angstrom. If the electronegativities of Cl and C are 3 and 2.5 respectively, find the CCl bond length according to Stevenson and Shoemaker formula. Now here's the trick. You have to find what? You have to find the CCl bond, that is D of AB you have to find, but you are not given directly R of A and R of B. You are given the CC single bond lengths and CL bond length as well. This is the first case of covalent. Remember, where D of AB upon 2 was equal to R of X, because they are like atoms. Okay, so by these formula we can find it. 1.54 by 2 will be what? It will be equal to 0.77 angstrom and 1.98 upon 2 will be equal to 0.99 angstrom. This is ARA, this is RB. Very simple. Just put the value here. So 0.77 plus 0.99 minus 0.09 into the difference of electronegativity. 3 minus 2.5, 0.5. Very easy. Just calculate it. You will get it equal to 1.715 angstrom. This is D of A. Got it? Very simple. Just put the formula. Just put the formula. You'll get the answer. Okay, let's move to the last question. The ASCL bond distance in ASCl3 is 2.2 angstrom. Estimate the single bond covalent radius known as SBCR of AS. Okay, we have to find the R of AS to be simple. Assume the electronegativity of both AS and Cl to be the same, that is delta X is equal to 0 here, and the radius of Cl is 1 angstrom. Okay, very simple question. D of AB will be equal to what? R of A plus R of B. That's it, because it is the case one. No formula like the shoemaker one. It was for when delta X was not tending to 0, but here delta X is tending to 0. So we'll use the simple formula, the first one formula. Now just put the value R of A, that is R of AS you have to find. R of B is given 1 angstrom. D of AB is given 2.2. Simply subtract R of AS will be what? 1.2 angstrom. Very easy. Got it? Okay, now comes the most important topic, that is trends in atomic radius. Whatever we have discussed up to this particular topic was for this topic only. Okay, questions comes from this only. The chance of question coming from those topics or those numericals are very low, but they were important to understand these trends in atomic radius. So what are the trends in atomic radius in our periodic table? When you move in period, what happens? Number of electrons increases, number of electron increases, which leads to increase in Z effective. How? Because number of electrons are increasing in the outer shell. Okay, outer shell are getting more and more electrons, for which the inner electrons repulsion force is getting distributed. Okay, this distribution causes the overall reduction in Z effective. Increase in Z effective. This increase in Z effective leads to what? Decrease in radius, decrease in atomic radius. So in going in any period, the atomic radius, what happens? It decreases. If we go in the group that is top to bottom, what happens? The orbitals increases. The orbital, it increases, sorry for the spelling, the orbital increases, which leads to increase in radius. This is very simple. Orbital outer shell is increasing, so radius will increase. Got it? Okay, but it is not this simple. There are few exceptions to this trend in atomic radius, and that is important for exam. Okay, question come from those exceptions as well. So there are 4 exceptions that we are going to discuss here. Let's look at those 4 exceptions. Okay, here come the very first exception in atomic radius, that is inert gas. What it is? It states that the radius of inert gas is given largest in the period. Let's go back to periodic table. These inert gases now, their radius is largest in the entire period. Okay, they're breaking this particular rule. It is an exception case. So for example, for the first period, hydrogen and helium will be larger. In second period, neon will be the largest, followed by lithium, beryllium, boron, carbon, and so on, nitrogen, and so on. Similarly, in third period, argon will be largest, followed by sodium, magnesium, the same period. Okay, this is the exception. The atomic radius of inert gases is largest. Why it is so? It is because of van der Waals radius. In case of inert gases, van der Waals radius comes into play, and we already know that van der Waals radius is greater than all 3 of them. Now, it is greater than metallic, it is greater than covalent. Hence, van der Waals radius comes into play, and inert gases has got highest atomic radius. Okay. The second exception is 3D series. This is the expectation. While going in 3D series, scandium, titanium, simple, but after chromium, it changes. The atomic radius starts to get equal. Okay. This is very important. Remember this thing. And after this, zinc size increases suddenly. Now you must be wondering why it is happening. It is happening because of addition of electrons in outer shell. Here in the formula, Z effective is equal to Z minus sigma. Z was dominating, but after this particular point, this starts to dominate. The outer electrons gets too much that this sigma starts to dominate Z, and the Z effective becomes equalized, which leads to equal atomic radius. And after this, the sigma becomes this large that Z effective starts to get decreases, which led to increase in size of zinc. Got it? So remember this. This is very important. Let's move on to third. That is radius of aluminium is equal to radius of gallium. Okay, let's go back to our periodic table. Here is aluminium. Here is gallium. How can they be equal? Because of D subshell. What it is? When adding electrons to gallium, D subshell gets filled here, but its screening effect is really poor. D subshell's screening effect is highly poor. D and F both. This poor screening effect leads to decrease in size, leads to domination of attraction force here, which makes the radiuses of aluminium and gallium what equal. Okay, from this particular thing we also understand that SPDF, this is the sequence for screening effect. Okay, they have got good screening effect and they have poor screening effect. Got it? Okay, let's move further. Fourth and the last exception, radius of 4D series is equal to radius of 5D series, again because of screening effect. In 5D series, poor screening effect happens because of 4F electrons, and these leads to decrease in size, which leads to same radius of 4D and 5D series. Got it? These explanations are not that important. You are just supposed to remember the exceptions, because that is what comes in exam, and you will have to calculate via those exceptions only. You have to remember them.